19,000 light-years from Earth, a star burns with a diameter so vast that if you placed it where our Sun sits, its surface would extend beyond the orbit of Saturn. Light would take 9 hours to travel from one side to the other. This is Stephenson 218, and it may be the largest star humanity has ever discovered. The volume of this single stellar object could contain 10 billion suns. Its photosphere, the visible surface where light escapes into space, encompasses a region of space larger than our entire inner solar system. Every planet from Mercury to Jupiter would orbit inside the star itself, vaporized within an atmosphere so tenuous that its outer layers barely qualify as matter by terrestrial standards. For decades, astronomers have searched for the physical limits of stellar size, cataloging red supergiants and hypergiants pushing the boundaries of what stellar physics allows. Betelgeuse, the famous red giant marking Orion's shoulder, extends 764 times the Sun's radius. UY Canis Majoris, once considered the largest known star, reaches approximately 1,420 solar radii. UY Scuti, discovered in 1860 but only recently measured accurately, extends to roughly 1,708 solar radii. Each discovery seemed to push the limits further, suggesting stars could grow arbitrarily large given sufficient mass and the right evolutionary conditions. Then came Stephenson 218. Stephenson 218 resides in Stephenson 2, one of the most massive open star clusters in the Milky Way galaxy. The cluster contains 26 red supergiants, an extraordinary concentration of evolved massive stars rarely found together among these giants. Stephenson 218 stands apart. Initial measurements suggested a radius of approximately 2,150 solar radii, making it roughly 60% larger than any previously measured star. If confirmed, this would place Stephenson 218 at the theoretical maximum size a star can achieve before becoming gravitationally unstable and tearing itself apart. The star exists at the edge of physical possibility, but measuring the size of such distant, enormous objects is extraordinarily difficult. Stephenson 218 lies embedded in dense molecular clouds and dust that obscure it at visible wavelengths. Direct angular diameter measurements, the gold standard for determining stellar size, require interferometry at infrared wavelengths where dust absorption is reduced. The star's extreme brightness in infrared, its variable nature, and uncertainty about its distance from Earth all introduce substantial error bars. Different studies have published radius estimates ranging from 1,800 to 2,200 solar radii. The star is unquestionably among the largest known, but whether it truly holds the record remains uncertain. What is certain is that stars like Stephenson 218 should not exist for long. Red supergiants and hypergiants are the final evolutionary phase of massive stars before they explode as supernovae. These stars burn through their nuclear fuel at prodigious rates, fusing hydrogen, helium, and heavier elements in their cores in a desperate attempt to generate enough pressure to counteract gravitational collapse. The largest stars have the shortest lives. While the Sun will shine for 10 billion years, stars like Stephenson 218 exhaust their fuel in mere millions of years, a cosmic eye blink. The fact that we can observe Stephenson 218 at all means we are witnessing a rare, fleeting phase of stellar evolution. The star's enormous size arises from its extreme luminosity and low surface temperature. Stephenson 218 radiates approximately 440,000 times more energy than the Sun, though estimates vary widely from 300,000 to 630,000 solar luminosities depending on assumptions about distance and extinction from interstellar dust. This energy output drives powerful stellar winds that blow off the star's outer layers, carrying away several Earth masses of material each year. As the star loses mass, its envelope expands to enormous proportions. The outer atmosphere becomes so diffuse, with densities millions of times lower than Earth's atmosphere, that the traditional boundary between star and space becomes ambiguous. Where exactly does Stephenson 218 end and the vacuum of space begin? Determining the star's mass presents similar challenges. Mass cannot be measured directly for isolated stars like Stephenson 218. Instead, astronomers infer mass from luminosity using stellar evolution models. These models suggest the star originally formed with approximately 16 to 25 solar masses, though it may have lost significant mass through stellar winds over its lifetime. The current mass might be substantially lower than the birth mass, perhaps 12 to 18 solar masses remaining. This creates an unusual situation where the star's physical size vastly exceeds what its mass would normally produce. The star is enormous but not particularly massive. A bloated shell of gas held together by gravity so weak that the escape velocity at the photosphere is comparable to the orbital velocity of the stellar winds. These extreme properties make Stephenson 218 a natural laboratory for testing stellar physics at its limits. How does nuclear fusion operate in cores where temperatures exceed 100 million Kelvin and densities approach 100,000 kilograms per cubic meter? How do convection currents transport energy through envelopes hundreds of millions of kilometers thick? What determines the maximum size a star can achieve before radiation pressure and stellar winds stir away its outer layers faster than fusion can generate energy? Why do some massive stars become compact blue supergiants while others expand to red hypergiant dimensions? Stephenson 218 offers clues to these questions. Tonight, we will journey inside this stellar colossus to understand what makes it so large, how astronomers measure such distant giants, why stars this size exist at all, and what fate awaits Stephenson 218 in its final moments. We will compare it to other stellar giants, explore the physics governing its structure, examine the observational techniques revealing its properties, and place it in the cosmic context of stellar evolution and the limits nature imposes on astronomical objects. Along the way, we will discover that the question "how big is Stephenson 218 really?" has no simple answer, reflecting deep uncertainties in astronomy and fundamental questions about what we mean by size for an object without a defined boundary. Before we begin this journey to the largest star, if you are fascinated by stellar extremes, cosmic scale, and the observational astronomy revealing the universe's most remarkable objects, subscribe and give this video a thumbs up. And here is a question: if you could observe any single moment in Stephenson 218's remaining life, from now until its inevitable supernova, which phase would you choose and why? Comment below. I will pin the most creative answer. The scale of Stephenson 218 challenges human comprehension. We evolved to understand objects measured in meters and kilometers, distances we can walk or drive. A star 2,000 times wider than the Sun, occupying a volume that could hold 10 billion solar equivalents, exists beyond intuitive grasp. Yet through mathematics, physics, and careful observation, we can understand such objects, measure their properties, predict their behavior, and place them in the grand narrative of cosmic evolution. Now let's begin. Crimson Colossus Stephenson 218 belongs to the class of red supergiants, the largest type of star in the universe by physical volume. Red supergiants represent a late evolutionary stage for stars born with approximately 8 to 40 solar masses. These stars begin life as hot, blue, compact objects fusing hydrogen in their cores. After millions of years, the core hydrogen depletes, and the star transitions to helium fusion, triggering an expansion that transforms it into a supergiant. The outer layers swell to hundreds or thousands of times the original radius while the surface cools from 30,000 Kelvin to below 4,000 Kelvin, shifting the star's color from blue-white to orange-red. Stephenson 218 has a surface temperature estimated between 3,200 and 3,600 Kelvin, similar to a glowing coal or the heating element in an electric stove. This relatively cool temperature means the star radiates most of its energy in infrared wavelengths invisible to human eyes. If you could somehow survive near Stephenson 218, the star would appear as a dim orange-red disk despite its enormous luminosity. The cool temperature also allows molecules to form in the star's outer atmosphere, including titanium oxide, which creates broad absorption bands in the spectrum and contributes to the characteristic red color. The star's luminosity, the total energy it radiates per second, is approximately 440,000 times the Sun's luminosity, though estimates range from 300,000 to 630,000 solar luminosities. This uncertainty arises from multiple factors. Luminosity calculations require knowing the star's distance from Earth and the amount of light absorbed by interstellar dust between the star and our telescopes. Distance uncertainty directly propagates to luminosity uncertainty since brightness decreases with the square of distance. If Stephenson to 218 is farther than assumed, it must be intrinsically brighter to appear as bright as observed, and vice versa. Stephenson to 218 lies in the constellation Scutum, near the plane of the Milky Way where star density and interstellar dust are both high. The star is not visible to the naked eye despite its enormous luminosity because dust extinction reduces its apparent brightness by many magnitudes at visible wavelengths. Only in infrared wavelengths, where dust is relatively transparent, does the star become prominent. The cluster Stephenson to that contains it was first catalogued in 1990 by Charles Bruce Stephenson, who identified it as a concentration of infrared bright objects. Follow-up spectroscopy revealed the cluster contains numerous red supergiants at similar distances, confirming it as a genuine stellar association rather than a chance alignment. The cluster's distance is estimated at approximately 19,000 light-years, placing it on the far side of the Milky Way's Scutum Centaurus arm, one of the galaxy's major spiral arms. This distance estimate comes from multiple methods, including main sequence fitting, where the apparent brightness of ordinary stars in the cluster is compared to their known absolute brightness to infer distance, and from spectroscopic parallax, where spectral features indicate the intrinsic luminosity of stars, allowing distance calculation from apparent brightness. These methods agree reasonably well, giving confidence in the 19,000 light-year figure, though uncertainties of 10 to 20% remain possible. At this distance, Stephenson 218's angular diameter, how large it appears on the sky, is incredibly tiny despite its enormous physical size. The star subtends an angle of roughly 0.8 milliseconds, comparable to viewing a beach ball from 10,000 kilometers away. This minuscule angular size makes direct measurement extraordinarily challenging. Even the largest telescopes cannot resolve the star as anything but a point source using conventional imaging. Only interferometry, combining light from multiple telescopes to synthesize a larger effective aperture, can measure such small angles. The physical radius calculation combines the angular diameter measurement with the distance estimate. If the star's angular diameter is 0.8 milliseconds and its distance is 19,000 light-years, geometry gives a physical radius of approximately 2,150 times the Sun's radius, or about 1.5 billion kilometers. To put this in perspective, light traveling at 300,000 kilometers per second takes 8 minutes to reach Earth from the Sun's surface but would take about 83 minutes, nearly an hour and a half, to travel from Stephenson to 218's center to its surface. The star is so large that its radius measured in light minutes exceeds the Sun's radius measured in light seconds by a factor of over 600. If Stephenson to 218 replaced the Sun at the center of our solar system, the results would be catastrophic. Mercury, with an orbital radius of 58 million kilometers, would be deep inside the star's envelope, as would Venus at 108 million kilometers and Earth at 150 million kilometers. Mars, orbiting at 228 million kilometers, would sit approximately at the star's surface or slightly outside depending on the exact radius estimate. Jupiter at 778 million kilometers would be the first planet safely beyond the photosphere, though it would experience temperatures hot enough to vaporize rock and metal. Saturn at 1.4 billion kilometers would orbit just outside the star if the radius is close to the upper estimates of 2,200 solar radii. The volume of Stephenson to 218 is proportional to the cube of its radius. A star 2,150 times the Sun's radius has a volume approximately 10 billion times greater. Imagine filling the Sun with spherical volumes the size of Earth. You could fit approximately 1.3 million Earths inside the Sun. Stephenson to 218 could hold 1.3 million times 10 billion, or 13 trillion Earths. The number is so large it loses meaning. For scale, the entire human population, nearly 8 billion people, could each be assigned 1,600 planets the size of Earth, all fitting within Stephenson to 218 with room to spare. Yet despite this enormous volume, Stephenson 218's mass is not proportionally gigantic. Stellar evolution models suggest a current mass between 12 and 18 solar masses. Perhaps originally 16 to 25 solar masses at birth with significant mass loss through stellar winds. This means the star's average density is extraordinarily low. The Sun's average density is about 1,410 kilograms per cubic meter, roughly 40% denser than water. Stephenson 218's average density is approximately 1/10 billionth of the Sun's, around 0.001 kilograms per cubic meter, about 1/10,000th the density of Earth's atmosphere at sea level. This density is so low that the outer regions of Stephenson 218's atmosphere are essentially a near vacuum by terrestrial standards. In the outermost layers of the photosphere, the density might be 100 million times less than Earth's atmosphere, comparable to the density at an altitude of 100 kilometers above Earth's surface where the atmosphere transitions to space. You could, in principle, fly a spacecraft through the outer layers of Stephenson 218 with relatively little resistance, though the intense radiation and heat would destroy any known materials instantly. The star's structure consists of distinct layers, each characterized by different physical conditions and processes. At the center lies the core, a region perhaps 100 million kilometers in radius, where nuclear fusion generates energy. Temperatures in the core exceed 100 million Kelvin, hot enough to fuse helium into carbon and oxygen. The core's density reaches 100,000 kilograms per cubic meter or higher, comparable to lead, where matter exists in a plasma state with electrons stripped from atomic nuclei. Surrounding the core is the envelope, a thick layer hundreds of millions of kilometers deep where energy generated in the core is transported outward primarily through convection. Convection in stars occurs when energy transport by radiation becomes inefficient due to high opacity, the tendency of matter to absorb photons. In red supergiants, the cool outer layers have high opacity because partially ionized atoms form, especially hydrogen and helium, which absorb photons readily. Energy cannot escape through radiation, so temperature gradients build up. When the gradient becomes steep enough, convection begins. Hot plasma rises from the interior, cools by radiating energy at the surface, and descends back down. This creates massive circulation cells, some as large as the distance from the Sun to Mars, churning through the star's envelope at velocities exceeding 30 kilometers per second. The photosphere, the visible surface of the star, represents the layer where optical depth, the likelihood that photons can escape to space, drops to unity. Below the photosphere, photons are absorbed and re-emitted many times, trapped in the star's interior. Above the photosphere, photons travel freely through space. The photosphere is not a solid surface but rather a transition zone, perhaps a few thousand kilometers thick, where conditions shift from opaque to transparent. For a star as large as Stephenson 218, this transition occurs at densities millions of times lower than Earth's atmosphere, and what we would consider a hard vacuum. Above the photosphere lies the chromosphere and potentially an extended atmosphere or wind region where gas flows outward, escaping the star's gravity. Spectroscopic observations of red supergiants often reveal evidence of extended atmospheres with complex structures including density enhancements, cooler and hotter regions, and molecular absorption from species like water vapor and carbon monoxide that form in the cooler outer layers. Some red supergiants show evidence of enormous convective cells reaching the surface and creating bright spots or asymmetric structures visible in high-resolution imaging. Stephenson 218's extreme size places it near the theoretical limit for stellar radii. The Hayashi limit, named after Japanese astrophysicist Toshiro Hayashi, defines a boundary in the temperature-luminosity diagram beyond which stars cannot exist in hydrostatic equilibrium. Stars cooler than the Hayashi limit for their luminosity become fully convective and dynamically unstable. Stephenson 218 sits close to this limit. If it were any larger and cooler, the star would not be able to transport energy from core to surface efficiently enough to maintain equilibrium, and it would pulsate violently or shed its outer layers completely. The star's position near this limit suggests it may be unstable, varying in size and luminosity on timescales of months to years. Many red supergiants and hypergiants exhibit variability, brightening and dimming as they pulsate or as convective cells create temporary bright regions. Observations of Stephenson to 218 are limited by its faintness at visible wavelengths and its location in a crowded star field, making long-term monitoring difficult. Whether it is currently stable or undergoing variations that might change its size significantly remains uncertain. Understanding Stephenson to 218 requires grasping the tension between its enormous size and the physical forces trying to compress or disrupt it. Gravity pulls inward, trying to collapse the star. Radiation pressure from fusion in the core pushes outward. Convection transports energy, creating dynamic motions that resist compression. Stellar winds carry away mass, reducing the gravity holding the envelope. These forces achieve a delicate, temporary balance, allowing the star to exist in its current configuration. But this balance is fragile, sustained only by nuclear fusion that will inevitably exhaust its fuel, leading to catastrophic collapse and supernova explosion. Discovery Journey. The path to discovering and measuring Stephenson to 218 reflects the evolving capabilities of astronomical technology and the challenges inherent in studying the most extreme objects in the universe. The story begins not with Stephenson to 218 specifically, but with the identification of its host cluster, Stephenson 2. A remarkable concentration of red supergiants that would eventually yield multiple candidates for the title of largest star. Charles Bruce Stephenson, an astronomer at the Case Western Reserve University Warner and Swazi Observatory, conducted systematic surveys of the Milky Way in the late 20th century, searching for unusual stellar objects. Using photographic plates and spectroscopy, Stephenson identified clusters and associations of massive stars, cataloging them for future study. In 1990, his survey revealed a grouping of bright infrared sources in Scutum, designated Stephenson 2. Initial observations showed the cluster contained numerous red supergiants, an unusual finding since such evolved massive stars are relatively rare, and finding many together is statistically unlikely unless they formed together in a single burst of star formation. Follow-up observations confirmed Stephenson 2 as one of the most massive open clusters in the Milky Way. Open clusters, unlike globular clusters which contain hundreds of thousands to millions of old stars, are loose associations of young to middle-aged stars formed from the same molecular cloud. Most open clusters contain a few hundred to a few thousand stars, but Stephenson 2 is exceptional. Estimates suggest the cluster originally formed with perhaps 100,000 solar masses of stars, making it comparable to young massive clusters observed in other galaxies. Most of the original stars were low mass and have dispersed or become difficult to detect, but the cluster's massive stars, which evolve quickly, remain concentrated and visible as red supergiants. 26 red supergiants have been identified in Stephenson 2, an extraordinary number. The cluster's age is estimated at 14 to 20 million years, precisely the epoch when stars in the 10 to 30 solar mass range transition from main sequence to red supergiant phase. Lower mass stars have not yet evolved, while higher mass stars have already exploded as supernovae. This age window explains the cluster's red supergiant population, but it also means Stephenson 2 is doomed. Within the next few million years, all these red supergiants will explode, leaving behind neutron stars and black holes. The cluster will gradually disperse, its stars scattering through the galaxy, erasing the evidence of the massive star formation event that created it. The individual stars in Stephenson 2 were numbered sequentially, with Stephenson to 218 being the 18th catalogued object. Initial photometry and spectroscopy indicated it was a red supergiant with characteristics similar to other cluster members, but early observations did not immediately single it out as the largest. Determining size requires measuring angular diameter, a capability that became widely available only with the development of infrared interferometry in the early 21st century. Interferometry combines light from multiple telescopes to synthesize an effective aperture equal to the separation between the telescopes, achieving angular resolution far superior to any single telescope. The technique has been used in radio astronomy since the 1950s, but extending it to infrared and optical wavelengths required technological advances in stable baselines, precise timing, and atmospheric correction. Facilities like the Very Large Telescope Interferometer in Chile and the CHAR array in California made high-resolution stellar observations possible. enabling direct measurement of stellar diameters for nearby bright stars. For distant, obscured objects like Stephenson to 218, measurements remained extremely challenging. The first estimates of Stephenson 218 size came from combining photometry at multiple wavelengths with stellar atmosphere models. By measuring the star's brightness in infrared bands and fitting the observed spectrum to models of red supergiant atmospheres, astronomers could infer the effective temperature. Combining temperature with total luminosity, derived from the star's apparent brightness and estimated distance, allows calculation of radius through the Stefan-Boltzmann law, which relates luminosity to temperature and surface area. This indirect method provided initial estimates suggesting Stephenson to 218 was among the largest stars in the cluster, with a radius exceeding 2,000 solar radii. Subsequent attempts to measure the angular diameter directly faced multiple obstacles. The star's location in the galactic plane means observations must contend with significant atmospheric water vapor absorption at infrared wavelengths, requiring observations from high-altitude sites or space-based telescopes. The star's embedding in molecular clouds creates circumstellar extinction that varies with wavelength, complicating the conversion from observed brightness to intrinsic luminosity. Variability in the star's brightness and size over time means measurements at different epochs may yield different results. Not because the measurements are wrong, but because the star genuinely changes. A 2013 study using photometry and spectroscopy from multiple sources provided revised estimates of the properties of several Stephenson to red supergiants, including Stephenson to 218. This study used improved distance estimates for the cluster and better models of interstellar extinction to derive luminosities and radii. The results place Stephenson to 218's radius at approximately 2,150 solar radii with an uncertainty of about 150 solar radii, making it potentially the largest known star, but with enough uncertainty that other candidates, like UY Scuti, remain competitive. Controversies and revisions characterize the history of measuring the largest stars. Canis Majoris held the record for years with radius estimates exceeding 2,000 solar radii before better measurements revised the radius downward to about 1,420 solar radii. UY Scuti was announced as the largest known star in 2012 with a radius of 1,708 solar radii. The earlier estimates had been even larger. Canis Cygni, another red supergiant, has been proposed as a competitor with estimates around 1,420 to 2,850 solar radii depending on assumptions. Scorpii, Westerland 1 to 26. And several other hypergiants have similarly large size estimates with significant uncertainties. The pattern reveals a fundamental challenge: measuring stellar radii for distant, obscured, variable red supergiants and hypergiants is extraordinarily difficult, and published values often have error bars of 20% or more. When two stars' measurements overlap within their uncertainties, declaring one definitively larger than the other becomes impossible. Stephenson the 2nd to the 18th of May be the largest, or UY Scuti might be, or perhaps another star not yet measured with sufficient precision. The current state of knowledge allows only that Stephenson to 218 is among the largest known stars, likely within the top 3, possibly the largest, but not proven beyond doubt. Improving these measurements requires better observational techniques. Future interferometric observations with next-generation facilities could achieve millisecond angular resolution at infrared wavelengths, directly imaging the disks of stars like Stephenson to 218 and measuring their diameters without relying on model-dependent indirect methods. Space-based infrared telescopes like the James Webb Space Telescope, while not designed for interferometry, can observe red supergiants at infrared wavelengths without atmospheric absorption, providing better photometry for modeling. Another approach involves astroseismology, studying oscillations in a star's brightness or radial velocity to infer internal structure and size. Stars pulsate in characteristic modes determined by their size, mass, and composition. Detecting and analyzing these oscillations provides model-independent constraints on stellar parameters. Some red supergiants exhibit low-frequency oscillations consistent with radial pulsation or convect timescales. If Stephenson to 218 shows detectable oscillations, Analysis could yield an independent radius estimate. The challenge extends beyond technology too. Fundamental physics. Red supergiants like Stephenson to 218 do not have well-defined surfaces in the classical sense. The photosphere is a fuzzy boundary where optical depth transitions from opaque to transparent, but this boundary's location depends on wavelength. Observing at different infrared bands probes different depths in the atmosphere, potentially measuring different radii. Extended atmospheres, stellar winds, and circumstellar dust shells further blur the boundary between star and space. When we measure the size of Stephenson to 218, exactly what are we measuring? The answer depends on operational definitions and observational techniques, introducing irreducible ambiguity. Despite these uncertainties, the observational constraints clearly indicate Stephenson to 218 is extraordinarily large, pushing against the theoretical limits for stellar size. Whether it ranks as number 1, 2, or 3 among known stars matters less than what it represents: a natural laboratory for extreme stellar physics, an object testing the boundaries of what nature permits, and a spectacular example of the universe's capacity to create structures dwarfing human intuition. The ongoing effort to measure it precisely drives improvements in observational astronomy and deepens understanding of stellar evolution at its most dramatic. The history of discovering and measuring stellar giants like Stephenson to 218 also illustrates the cumulative nature of astronomical knowledge. Early generations of astronomers identified bright stars and cataloged their positions. Later astronomers measured distances, brightnesses, and spectra. More recent work uses sophisticated technology to resolve stellar surfaces and measure diameters directly. Each generation builds on previous work, refining measurements, correcting errors, and pushing the boundaries of what can be known. Stephenson to 218 represents the current frontier. But future discoveries will surely reveal even more extreme objects or refine our understanding of current record holders, continuing the long tradition of expanding human knowledge of the cosmos. Comparative giants. Understanding Stephenson to 218's true scale requires comparing it to other stellar giants, placing it within the population of red supergiants and hypergiants that define the upper limits of stellar size. The universe contains a hierarchy of stellar objects ranging from brown dwarfs barely massive enough to fuse deuterium to hypergiants thousands of times larger than the Sun. Stephenson to 218 occupies the extreme end of this distribution, but it does not stand alone. Several dozen stars compete for the distinction of largest known stellar object, each presenting unique observational challenges and physical characteristics. Betelgeuse, perhaps the most famous red supergiant due to its prominent position in Orion and its recent dramatic dimming event, serves as a useful baseline for comparison. Betelgeuse has a radius of approximately 760 for solar radii, less than half Stephenson 218's estimated size. If Betelgeuse replaced the Sun, its surface would extend to Mars's orbit. The star is close enough, at about 548 light-years, that its angular diameter can be measured directly by multiple techniques. And high-resolution imaging has revealed surface features including giant convective cells and asymmetric brightness variations. Betelgeuse's well-studied properties make it a calibration point for understanding more distant red supergiants. Antares, another prominent red supergiant visible to the naked eye in Scorpius, has a radius of about 680 solar radii, similar to Betelgeuse. Antares lies approximately 550 light-years from Earth and has been studied extensively due to its brightness and accessibility. The star has a binary companion, a hot blue star that creates an interesting contrast in color when observed telescopically. Antares' mass is estimated at 12 to 15 solar masses, with a luminosity about 75,000 times the Sun's. Comparing Antares to Stephenson to 218 highlights how much larger and more luminous the extreme hypergiants are compared to more typical red supergiants. UY Canis Majoris, located about 3,800 light-years away in the constellation Canis Major, held the title of largest known star for many years before better measurements revised its size downward. Current estimates place UY Canis Majoris' radius at approximately 1,420 solar radii. making it about 2/3 the size of Stephenson 218 but still enormous by most standards. The star's luminosity is approximately 300,000 solar luminosities, and its mass is estimated between 17 and 25 solar masses. Canis Majoris exhibits dramatic mass loss, ejecting about 30 times Earth's mass every million years through a powerful stellar wind. The circumstellar environment contains complex structures including arcs, knots, and filaments visible in high-resolution infrared images. Evidence of episodic mass ejection events over the past 1,000 years. UY Scuti, discovered in 1860 by German astronomers but only recently characterized accurately, has a radius of approximately 1,708 solar radii according to 2012 measurements. The star lies about 9,500 light-years away in Scutum, not far from Stephenson 218. UY Scuti's luminosity is estimated at 340,000 solar luminosities, and the star pulsates with a period of about 740 days, varying in brightness by more than a magnitude. The pulsations cause the radius to change by 10% or more, meaning the star's size depends on when you measure it. At maximum expansion, UY Scuti may exceed Stephenson 218's size, while at minimum it would be significantly smaller. This variability complicates direct comparison. Westerlin 1-26, a red supergiant in the Westerlin 1 superstar cluster approximately 11,500 light-years away, has a radius estimated between 1,530 and 2,550 solar radii depending on assumptions about the cluster's distance and the star's properties. The large uncertainty makes it impossible to determine whether Westerlin 1-26 is larger or smaller than Stephenson 218. What is clear is that Westerlin 1-26 is exceptionally luminous, radiating about 380,000 times the Sun's luminosity, and it exhibits irregular variability suggesting dynamic instabilities in its structure. KY Cygni, or red supergiant in Cygnus lying approximately 5,000 light-years away, has published radius estimates ranging from 1,420 to 2,850 solar radii. An enormous uncertainty reflecting the difficulty of measuring this highly obscured star. Different studies using different methods and assumptions yield vastly different results. Some measurements suggest KY Cygni rivals or exceeds Stephenson 218. while others place it significantly smaller. Until better observational constraints are available, KY Cygni's size remains poorly determined. Scorpii, a semi-regular variable red supergiant approximately 8,200 light-years away, has a radius estimated at about 1,411 solar radii. The star varies in brightness with periods of 714 and 1,040 days superimposed on longer-term changes, and its size likely varies correspondingly. Scorpii's luminosity is approximately 400,000 solar luminosities, making it intrinsically brighter than Stephenson 218 despite being smaller, suggesting a higher surface temperature of about 3,800 Kelvin compared to Stephenson 218's 3,200 to 3,600 Kelvin, RW Cephi. Another red supergiant with estimated radius between 1,260 and 1,610 solar radii exhibits dramatic variability and mass loss. The star is embedded in a circumstellar nebula created by ejected material, and spectroscopic observations show evidence of large-scale convection and atmospheric dynamics. RW Cephi's variability and uncertain distance make precise size determination difficult, but it clearly ranks among the largest known stars even if it does not hold the absolute record. Comparing these giants reveals patterns. All are red supergiants or hypergiants in late evolutionary stages. All have evolved from massive progenitor stars with initial masses between 10 and 40 solar masses. All exhibit significant mass loss through stellar winds, surrounding themselves with circumstellar material. Most show variability, either regular pulsations or irregular changes in brightness and size. None are particularly massive by stellar standards despite their enormous physical size, typically retaining only 10 to 25 solar masses after losing significant mass through winds. The luminosities cluster in a relatively narrow range, roughly 200,000 to 600,000 solar luminosities, despite the range in sizes. This reflects a relationship between luminosity, temperature, and radius. A star's luminosity is proportional to its surface area times the fourth power of its temperature. For a given luminosity, cooler stars must be larger to compensate for their lower temperature. The coolest red supergiants, with temperatures around 3200 Kelvin, achieve enormous sizes to radiate sufficient energy. Slightly hotter stars with temperatures around 3800 Kelvin are somewhat smaller for the same luminosity. This suggests that Stephenson 218's extreme size arises partly from being among the coolest known red supergiants. If accurate temperature estimates placing it at 3200 to 3400 Kelvin are correct, it must be extraordinarily large to generate its observed luminosity. Stars even cooler than this would likely become unstable, unable to transport energy efficiently from core to surface, making Stephenson 218's temperature close to the minimum physically possible for a star of its luminosity. The distribution of red supergiant sizes also reveals that stars larger than about 1,500 solar radii are rare. Most red supergiants have radii between 300 and 1,000 solar radii. The number of known stars decreases rapidly at larger sizes, with only a few dozen exceeding 1,500 solar radii and fewer than 10 exceeding 2,000 solar radii. This scarcity reflects both observational selection effects, as the largest stars are distant and difficult to measure, and genuine physical rarity, as stars at the size limit are unstable and short-lived, existing only briefly before exploding or shedding their envelopes. Interestingly, the largest stars are not necessarily the most massive. The most massive stars known, like our 136A1 in the Large Magellanic Cloud with an estimated mass over 200 solar masses, are blue hypergiants, not red supergiants. These extremely massive stars remain compact and hot, with radii only tens to hundreds of solar radii despite masses far exceeding Stephenson 218. The reason relates to stellar evolution pathways. Very massive stars may never expand to red supergiant dimensions, instead evolving through different phases or losing mass rapidly enough through powerful winds that they cannot develop extended envelopes. The existence of a maximum stellar radius appears to be a robust prediction of stellar physics. Stars larger than about 2,500 to 3,000 solar radii would have outer layers so loosely bound that radiation pressure and thermal expansion overcome gravitational binding. The envelope would not remain attached to the core but would disperse into space. Additionally, convection in such large stars becomes inefficient. The timescales for convective turnover, the time required for material to rise from the bottom of the convective envelope to the top, become comparable to or longer than the star's remaining lifetime. Energy cannot be transported to the surface fast enough, and the star either contracts or ejects its outer layers. Stephenson 218's size, approaching this theoretical maximum, suggests it may be fundamentally unstable. The star might undergo episodes of rapid mass loss, ejecting significant portions of its envelope in outbursts that temporarily reduce its size before the envelope re-expands. Observations of other large red supergiants show evidence of such behavior, with circumstellar nebulae containing clumps and shells indicating discrete ejection events. Whether Stephenson 218 exhibits similar behavior remains uncertain due to limited long-term monitoring. The quest to identify the largest star reflects both scientific interest and extreme physical conduct. Ions and human fascination with superlatives, astronomical records are frequently broken as observational capabilities improve and more of the sky is surveyed. Stephenson 218 currently holds a strong claim to the title of largest known star. But this record could be broken tomorrow if better measurements revise its size downward or if a new, even larger star is discovered in an ongoing survey. The transient nature of such records does not diminish their value. They mark the boundaries of current knowledge and motivate continued observation and study. Comparing Stephenson 218 to other stellar giants also contextualizes its significance. This star is not a bizarre outlier but rather an extreme example of a well-understood class of objects. The physics governing Stephenson 218 is the same physics governing Betelgeuse. just pushed to greater extremes. Understanding why some red supergiants become larger than others requires understanding the details of stellar evolution, mass loss, and envelope dynamics. Topics where much remains uncertain. Stephenson 218 provides a test case for theories of stellar structure at the most challenging regime. Measurement methods determining the physical size of a star 19,000 light-years away presents formidable observational and theoretical challenges. And like solar system objects that can be visited by spacecraft or nearby stars whose distances can be measured through annual parallax, distant stars like Stephenson 218 must be characterized entirely through analysis of the light they emit. The techniques astronomers employ to measure stellar radii fall into several categories, each with strengths, limitations, and sources of uncertainty that propagate through to the final size estimate. The most direct method is angular diameter measurement through interferometry. If you can measure the angular size a star subtends on the sky and know its distance, simple geometry gives the physical radius. The relationship is straightforward: linear size equals angular size times distance, with appropriate unit conversions. For Stephenson 218, the angular diameter is approximately 0.8 milliseconds, an angle so small that it represents 1/4500th of an arcsecond, which itself is 1/3600th of a degree. Measuring such tiny angles requires combining light from telescopes separated by hundreds of meters to achieve the necessary resolution. Interferometry exploits the wave nature of light. When light from a distant point source reaches to separated telescopes, the waves arrive with a phase difference determined by the baseline distance between the telescopes and the angular position of the source. Combining the light from both telescopes creates an interference pattern. If the source is not a point but has angular extent, the contrast of the interference fringes decreases. By measuring this fringe visibility as a function of baseline length and orientation, astronomers can reconstruct the angular size and even the shape of the source. For red supergiants observed in infrared wavelengths, interferometry provides the best direct size measurements. Facilities like the Very Large Telescope Interferometer in Chile combine light from multiple 8-meter telescopes to achieve effective angular resolution of a few milliseconds. However, observing Stephenson 218 with current interferometers is extremely difficult. The star's location low in the southern sky for Chilean observatories and its faintness at infrared wavelengths due to distance and dust extinction mean it is at the limit of detectability, even for the world's largest interferometers. An alternative approach uses photometry combined with stellar atmosphere modeling. If you measure a star's brightness at multiple wavelengths and fit the observed spectral energy distribution to theoretical models of red supergiant atmospheres, you can infer the effective temperature. The effective temperature is defined as the temperature a blackbody would need to radiate the same total energy per unit area as the star's surface. Once you know effective temperature and total luminosity, the Stefan-Boltzmann law gives the radius luminosity equals for pi times radius squared times the Stefan-Boltzmann constant times temperature to the fourth power. Solving for radius gives radius equals square root of luminosity divided by 4 pi times the constant times temperature to the fourth power. This method requires accurate luminosity determination, which depends on knowing the star's distance and the amount of interstellar extinction, the dimming caused by dust between the star and Earth absorbing and scattering light. Distance estimates for Stephenson 218 come from several techniques. The cluster Stephenson 2 contains main sequence stars whose absolute magnitudes can be estimated from their spectral types. Comparing these absolute magnitudes to observed apparent magnitudes gives a distance modulus, which converts to distance. Different studies have obtained distance estimates ranging from 17,000 to 20,000 light-years, with 19,000 light-years being a commonly adopted value. Extinction corrections are even more uncertain. Dust in the interstellar medium preferentially absorbs shorter wavelengths, making stars appear redder and dimmer than they intrinsically are. The amount of extinction depends on the quantity of dust along the line of sight and its properties. For Stephenson 218, located behind significant dust lanes in the galactic plane, extinction is substantial. Observations at multiple wavelengths, especially comparing optical to infrared brightness, constrain the extinction, but uncertainties of 20 to 30% are typical. Since luminosity depends on the extinction correction, these uncertainties propagate to the radius calculation. Effective temperature determination from spectral fitting introduces additional uncertainty. Red supergiant atmospheres are complex, with molecular absorption from titanium oxide, water vapor, and other species creating thousands of spectral lines. The observed spectrum depends not just on temperature but also on surface gravity, metallicity, and atmospheric structure. Models make simplifying assumptions, like one-dimensional stratified atmospheres and local thermodynamic equilibrium, that may not accurately represent the chaotic, freeze-dimensional convective atmospheres of real red supergiants. Different models can yield temperature estimates differing by several hundred Kelvin for the same star. A third method uses the star's variability to estimate size through pulsation theory. Many red supergiants pulsate radially, expanding and contracting with periods of months to years. The pulsation period relates to the star's average density through the period mean density relation. Period is proportional to square root of stellar radius cubed divided by mass. If you measure the pulsation period and estimate the mass from stellar evolution theory, you can infer the radius. However, Stephenson to 218's variability has not been well characterized due to limited long-term monitoring, making this method inapplicable at present. Combining multiple methods provides the most robust size estimates. If interferometry gives an angular diameter, photometric modeling gives an effective temperature and radius estimate, and the two results agree, confidence increases. If the methods disagree, it suggests problems with assumptions, like incorrect distance or extinction. For Stephenson to 218, interferometric measurements are marginal at best, so most published sizes rely on photometric modeling with assumed distances and extinction values. This makes the uncertainty large, typically plus or minus 200 to plus or minus 300 solar radii, or roughly plus or minus 10 to 15%. Systematic errors may exceed random statistical uncertainties. If the assumed distance is wrong by 10%, the derived luminosity is wrong by 21% since luminosity scales as distance squared, and the radius error is roughly 10% since radius scales as square root of luminosity. If the extinction correction is wrong, luminosity is affected proportionally, again impacting radius. If stellar atmosphere models do not accurately represent the star's temperature structure, the inferred effective temperature is wrong, and since radius depends on temperature to the power of -2 from the Stefan-Boltzmann law, a 10% temperature error causes a 20% radius error. Another complication is that red supergiants like Stephenson to 218 do not have sharply defined surfaces. The photosphere is a transition region, not a boundary. Observations at different wavelengths probe different optical depths, potentially measuring different radii. Infrared observations see deeper into the atmosphere where temperatures are higher and densities greater. Optical observations, if possible through the extinction, would see shallower layers. The true radius depends on which layer you define as the surface. Conventionally, astronomers define the photospheric radius as the layer where optical depth at a specific reference wavelength equals 2/3, but this is an operational definition, not a physical boundary. Extended atmospheres and stellar winds further blur the distinction between star and space. Spectroscopic observations of red supergiants often show emission lines from extended chromospheres and evidence of outflows at velocities exceeding escape velocity. Material in these regions is no longer gravitationally bound to the star but has not yet dispersed into the circumstellar environment. Should this material be considered part of the star? Different authors make different choices, contributing to discrepancies in published sizes. Circumstellar dust also affects observations. Many red supergiants, including potentially Stephenson to 218, are surrounded by dust shells formed when stellar wind material cools and molecules condense into solid grains. This dust absorbs starlight and re-radiates it at longer infrared wavelengths, creating excess infrared emission beyond what the stellar photosphere alone would produce. If not properly accounted for, this circumstellar emission causes overestimation of the stellar luminosity, leading to overestimated radius. Sophisticated modeling of the spectral energy distribution, including both stellar and circumstellar components, is necessary to separate the contributions. Despite these challenges, modern measurements of red supergiant Redi have achieved reasonable accuracy for well-observed nearby stars. Betelgeuse, for example, has been measured by multiple interferometric observations and photometric studies, with results generally agreeing within 10%. Extending these techniques to distant, obscure stars like Stephenson to 218 pushes the methods to their limits, but the fundamental physics is well understood. The primary obstacles are observational limited photons from faint distant sources, complex intervening dust, and insufficient angular resolution to directly image the stellar disk. Future improvements will come from multiple directions. Next-generation extremely large telescopes with 30 to 40 meter apertures will collect more light, enabling spectroscopy of faint distant red supergiants with sufficient signal-to-noise to constrain atmospheric models accurately. Space-based infrared telescopes avoid atmospheric absorption and achieve stable baselines for interferometry. Gaia, the European Space Agency's astrometry mission, is measuring precise parallax distances for millions of stars, potentially including Stephenson to cluster members, which would reduce distance uncertainty significantly. Improved stellar atmosphere models incorporating three-dimensional convection and non-equilibrium chemistry will provide more realistic temperature determinations. Long-term monitoring campaigns using automated survey telescopes will characterize the variability of red supergiants, revealing pulsation periods and amplitude variations that constrain mass and radius. Multi-epoch interferometry can track radius changes directly, separating mean radius from pulsational variations, combining all available data through sophisticated statistical analysis, properly accounting for correlated and systematic uncertainties, will yield the most accurate size estimates possible with current technology. For now, the best statement we can make about Stephenson to 218's size is that its radius is approximately 2,150 solar radii with an uncertainty of at least 10% and possibly 20%. Placing the true radius anywhere between 1,700 and 2,400 solar radii. This range encompasses the sizes of other leading candidates like UY Scuti and makes definitive ranking impossible. Stephenson to 218 is certainly among the 3 largest known stars, probably in the top 2, and quite possibly the largest, but conclusive proof requires better observations than currently available. Physical mechanisms. Understanding why Stephenson to 218 is so enormous requires examining the physical mechanisms that govern stellar structure and evolution, particularly the processes that allow some massive stars to expand to hypergiant dimensions while others remain compact. The fundamental principle is hydrostatic equilibrium, the balance between gravitational pressure pulling inward and thermal and radiation pressure pushing outward. For most of a star's life, this balance is maintained through nuclear fusion in the core generating heat and radiation that supports the overlying layers. When fusion can no longer provide adequate support, the balance shifts, triggering expansion or contraction depending on circumstances. Stephenson to 218 began life as a massive star, likely 16 to 25 solar masses, forming from a dense molecular cloud core approximately 14 to 20 million years ago based on its cluster's estimated age. Massive stars form differently than solar mass stars. The accretion process is more violent, with powerful stellar winds and radiation pressure from the forming protostar fighting against continued infall of material. Massive stars reach the main sequence, where they begin fusing hydrogen into helium, while still accreting material, and like lower mass stars that contract to the main sequence after accretion ends. On the main sequence, the star was much smaller than today, probably 15 to 20 solar radii, and far hotter, with a surface temperature around 30,000 to 35,000 Kelvin. The star appeared blue-white and radiated intensely in ultraviolet wavelengths. Core temperatures exceeded 30 million Kelvin, hot enough to fuse hydrogen via the CNO cycle, where carbon, nitrogen, and oxygen nuclei catalyze the fusion of 4 hydrogen nuclei into 1 helium nucleus. This process is extremely temperature sensitive, with fusion rates proportional to temperature to the 15th power or higher, concentrating energy generation in a small core region. The star's high luminosity on the main sequence, perhaps 200,000 solar luminosities, drove a powerful stellar wind even then. Radiation pressure, the outward force exerted by photons as they are absorbed by atoms, becomes extremely strong in massive stars. For stars above approximately 40 solar masses, radiation pressure approaches or exceeds gravitational binding for material at the surface. Line-driven winds, where photons are preferentially absorbed by metal ions like iron and magnesium, accelerate material to velocities exceeding 1,000 kilometers per second. Over millions of years, this wind mass loss removed significant mass from the star, possibly reducing Stephenson to 218's mass from 25 solar masses at birth to 20 solar masses by the time it left the mine. In sequence, after approximately 8 to 10 million years, the core hydrogen was exhausted. Fusion ceased in the core, and hydrogen fusion continued in a shell surrounding the now inert helium core. The core, no longer supported by fusion, contracted under gravity. This contraction released gravitational energy, heating the core and the surrounding shell. The increased temperature in the shell accelerated hydrogen fusion there, increasing the star's luminosity. Paradoxically, the star's envelope expanded enormously in response to the increased energy generation, transforming the star from a compact blue object to a swollen red supergiant. This expansion occurs because of changes in the star's opacity structure. The core contraction heats the deep interior, but the increased energy flux must travel through the envelope to escape. As energy flows outward, it encounters layers of partially ionized hydrogen and helium. Partially ionized atoms have high opacity, absorbing photons readily. The outer layers cannot transmit the energy flux through radiation alone. Temperature gradients build up, becoming steep enough to drive convection. The envelope becomes fully convective, with hot material rising from deep layers, radiating energy at the surface, cooling, and descending again. Convection is less efficient at transporting energy than radiation in most circumstances. The large energy flux from the core requires a large temperature gradient to drive sufficient convective flow. This gradient is achieved by having a large radius, allowing the temperature to drop gradually from the hot interior to the cool surface. The star expands to hundreds of times its original radius, with the surface temperature dropping to below 4,000 Kelvin. The expansion continues until a new equilibrium is established where convective energy transport can carry the luminosity from core to surface. When the core temperature reached approximately 100 million Kelvin, helium fusion ignited through the triple alpha process, where 3 helium nuclei combine to form carbon. Helium fusion releases substantial energy, approximately 10% as much per unit mass as hydrogen fusion, but the core's mass is limited. For Stephenson to 218, the helium core at ignition probably contained to 2 for solar masses. Helium fusion lasted approximately 1 million years, about 10% the duration of the main sequence phase, during which the star remained a red supergiant with properties similar to today. As helium depleted in the core, the pattern repeated. The helium core became inert carbon and oxygen, fusion continued in helium and hydrogen shells, the core contracted, and the envelope potentially expanded further. Carbon fusion ignited at about 600 million Kelvin, producing neon, magnesium, and other elements. This stage lasted only 12,000 years. Subsequent stages, neon fusion at 1.2 billion Kelvin and oxygen fusion at 1.5 billion Kelvin, became progressively shorter, 20 years and 4 years respectively. The star is currently in one of these late burning stages, perhaps oxygen burning, racing toward the final phase of silicon fusion that lasts only about 1 week before core collapse. Each successive fusion stage increases the core's temperature and density but decreases the energy generation rate per unit mass. The star's luminosity, set primarily by the shell burning rather than core processes, remains relatively constant at several 100,000 solar luminosities. The envelope structure adjusts to maintain energy transport, with the radius varying depending on the exact balance between energy generation, opacity, and convective efficiency. Stephenson 218's extreme size likely reflects its current position in the late stages of helium or post-helium burning. Theoretical models suggest that red supergiant would peak during or shortly after helium core exhaustion when shell burning reaches maximum intensity. The star may be in a transition phase, possibly undergoing thermal pulses where helium shell burning ignites episodically, causing temporary increases in luminosity and radius. Such pulses are predicted by stellar evolution models but are difficult to observe directly due to their irregular timing. Mass loss plays a critical role in determining how large the star can become. Strong stellar winds, driven by radiation pressure and pulsation-enhanced atmospheric levitation, remove mass from the surface at rates estimated between K-6 and 10 to 5 solar masses per year for red supergiants. Over a million years, this removes 1 to 10 solar masses, significantly reducing the star's total mass. Lower mass means weaker surface gravity, which makes the envelope easier to distend to large radii. The feedback loop between mass loss and radius is complex, with larger stars potentially losing mass faster due to lower escape velocity, but also becoming more extended as they lose mass, further reducing surface gravity. The Eddington limit provides a fundamental constraint on luminosity relative to mass. When radiation pressure equals gravitational force, material at the surface is no longer bound and escapes. For stars with solar composition, the Eddington luminosity is approximately 38,000 times the solar luminosity per solar mass. Stephenson to 218, with perhaps 15 solar masses and 440,000 solar luminosities, has a luminosity to mass ratio of about 29,000 solar luminosities per solar mass, approaching but not quite reaching the Eddington limit. This proximity to the Eddington limit drives strong mass loss and contributes to the star's extended envelope. Rotation, if significant, could affect the star's structure. Centrifugal force reduces effective gravity at the equator, potentially causing the star to bulge and preferentially lose mass from the equatorial regions. However, massive stars lose angular momentum through stellar winds, and by the time they reach red supergiant phase, rotation is typically slow. Observations of red supergiants show rotational velocities generally below 10 km per second, much slower than the tens to hundreds of kilometers per second observed in main sequence massive stars. Stephenson 218's rotation has not been measured, but it is likely slow and probably does not significantly affect the star's overall structure. Magnetic fields might influence the envelope structure and mass loss. Some red supergiants show evidence of large-scale magnetic fields from spectropolarimetry, though the fields are generally weak, a few Gauss or less compared to thousands of Gaussian magnetic chemically peculiar stars. Even weak fields could organize convective flows or channel stellar wind material along field lines, creating asymmetries in the circumstellar environment. Whether Stephenson to 218 has a significant magnetic field is unknown. The theoretical maximum radius for a red supergiant or hypergiant is set by several factors. Dynamical instability occurs when the envelope's binding energy becomes comparable to thermal energy, leading to ejection of outer layers. This happens when the radius exceeds approximately 3,000 solar radii for typical luminosities and masses. Convective instability arises when convection cannot transport energy efficiently, causing the envelope to become thermally unstable and potentially triggering large amplitude pulsations or eruptions. The Hayashi limit defines the coolest effective temperature possible for a given luminosity. Stars cannot exist in equilibrium cooler than this limit. Stephenson to 218, with radius around 2,150 solar radii and temperature around 3,300 Kelvin, sits near all these limits simultaneously. It is close to the maximum radius where the envelope remains bound. It operates near the Hayashi limit for its luminosity. It may be near the boundary where convection becomes inefficient. This suggests the star is in a precarious state, balanced at the edge of stability. Small perturbations, like changes in fusion rates or episodic mass loss events, could push it over the edge, triggering dramatic changes in structure or even catastrophic envelope ejection. The processes governing Stephenson to 218's structure are well understood in principle, described by equations of stellar structure and evolution that have been tested against countless observations of stars at various stages. But applying these equations to the most extreme objects, where approximations break down and instabilities emerge, remains challenging. Three-dimensional simulations of convection in red supergiant envelopes, including effects of rotation, magnetic fields, and pulsation. Requires supercomputers and still cannot capture all relevant physics. Understanding why Stephenson to 218 is so large requires combining observational constraints with theoretical models. Iterating between observation and theory to refine understanding of stellar physics in extreme regimes. Internal architecture. The interior structure of Stephenson to 218 differs dramatically from solar-type stars. With extreme physical conditions at the core and extraordinarily diffuse material in the outer envelope, creating a star that is simultaneously incredibly dense and incredibly tenuous depending on location. Understanding this internal architecture requires examining the star layer by layer, from the nuclear furnace at the center to the wispy outermost photosphere where the star fades into space. At the very center lies the core, perhaps 50 to 100 million kilometers in radius, roughly the size of Mercury's orbit or smaller. This region contains only a few solar masses of material but generates virtually all the star's energy. Current fusion processes, likely oxygen burning or possibly silicon burning depending on the star's exact evolutionary state, occur at temperatures exceeding 1.5 billion Kelvin. At these temperatures, atomic nuclei move so fast that they overcome electromagnetic repulsion and approach close enough for the strong nuclear force to bind them together, fusing lighter elements into heavier ones and releasing energy. The core's density is extraordinary, reaching 100,000 kilograms per cubic meter or higher, comparable to the density of iron or lead but in plasma form. Matter at these conditions exists as a fully ionized gas where electrons have been stripped from atomic nuclei by collisions. The electrons and nuclei form a dense soup, interacting through electromagnetic forces. Degeneracy pressure from electrons, arising from the Pauli exclusion principle that forbids multiple electrons from occupying the same quantum state, begins to contribute to supporting the core against gravity. Though thermal pressure remains dominant while fusion continues. Immediately surrounding the core are shell-burning regions where hydrogen and helium fusion continue in concentric layers. The helium-burning shell, perhaps located at a radius around 100 million kilometers, fuses helium into carbon and oxygen at temperatures around 100 to 200 million Kelvin. Outside this, the hydrogen-burning shell fuses hydrogen into helium at temperatures around 20 to 40 million Kelvin. These shells contribute significantly to the star's luminosity, sometimes exceeding the core's contribution during certain evolutionary phases. The temperature and density drop rapidly moving outward from the core. At a radius of 200 million kilometers, about the orbital distance of Mars in our solar system, temperatures have fallen to perhaps 10 million Kelvin and densities to 1,000 kilograms per cubic meter, comparable to the Sun's core. This region is radiative, with energy transported outward by photons diffusing through the plasma. Each photon undergoes billions of absorption and ray emission events, taking a random walk through the star. A photon created in the core might spend 100,000 years bouncing around inside the star before finally escaping to space. At some radius between 300 and 500 million kilometers, the envelope transitions from radiative to convective. Here, partial ionization of hydrogen and helium increases opacity dramatically. Photons cannot diffuse through this high-opacity material efficiently enough to carry the energy flux. Temperature gradients steepen until convection begins. Hot plasma rises from below, carrying energy through bulk motion rather than radiation. At the surface, the plasma radiates energy into space, cools, and descends back down. This convective envelope extends from the transition radius all the way to the photosphere at approximately 1.5 billion kilometers. The convective envelope is extraordinary in scale. Individual convection cells may span hundreds of millions of kilometers, larger than Earth's orbit around the Sun. Velocities in these cells reach 20 to 30 kilometers per second, comparable to Earth's orbital velocity. The convective turnover time, the duration for material to rise from the bottom of the envelope to the top, cool, and descend, is measured in years or decades. This slow turnover means the convection is not efficient at homogenizing composition or transporting angular momentum, creating the potential for chemical stratification and differential rotation within the envelope. Temperature decreases monotonically moving outward through the envelope. At the base of the convective zone, temperatures might be a few million Kelvin. At 500 million kilometers radius, temperatures have dropped to perhaps 100,000 Kelvin. At 1 billion kilometers, temperatures fall below 10,000 Kelvin. In the photosphere at 1.5 billion kilometers, temperatures finally reach the 3,200 to 3,600 Kelvin observed from outside. The temperature gradient is relatively gentle compared to the Sun because the envelope is so extended, with temperature dropping by a factor of 1,000 over a radius that spans billions of kilometers. Density falls even more dramatically. At the base of the convective zone, densities might be around 100 kilograms per cubic meter, roughly the density of cork. At half the photospheric radius, densities have fallen to around 1 kilogram per cubic meter, comparable to air. At the photosphere itself, densities are approximately 0.001 kilograms per cubic meter, about 1/10,000th the density of Earth's atmosphere at sea level. The outermost layers are essentially a hard vacuum by terrestrial standards, yet they are still hot enough to glow brightly and thick enough to be opaque to visible light. The pressure structure follows from temperature and density through the ideal gas law. Pressure equals density times temperature times the gas constant divided by mean molecular weight. At the core, pressures reach gigapascals or higher, billions of atmospheres. At the photosphere, pressures drop to around 10 pascals, about 1/10,000th of Earth's atmospheric pressure. The star's internal pressure at various radii exactly balances the weight of overlying material, maintaining hydrostatic equilibrium. This balance is extraordinarily sensitive. A 1% change in core temperature would lead to rapid expansion or contraction until a new equilibrium is established. The composition varies throughout the star. The core has been heavily processed through nuclear fusion, with the original hydrogen and helium converted into heavier elements. The exact composition depends on the current burning stage. If oxygen burning is occurring, the core consists primarily of oxygen, silicon, sulfur, and other intermediate mass elements, with an iron core beginning to form at the very center. Outside the burning shells, composition transitions to helium with some carbon and oxygen mixed in from convective dredge-up. The outer envelope retains approximately the original composition from the star's birth, about 70% hydrogen, 28% helium, 2% heavier elements by mass. Convective mixing periodically brings fusion products from deep in the star to the surface, a process called dredge-up. This occurs during certain evolutionary phases when convection penetrates into regions previously enriched by fusion. Spectroscopic observations of red supergiants often show surface enhancement of carbon, nitrogen, and other CNO-processed elements, evidence of dredge-up. Whether Stephenson 218 has undergone dredge-up is unknown, as detailed spectroscopy has not been published, but it is likely based on comparison with similar stars. The energy generation and transport mechanisms create the star's luminosity profile. Most energy is generated in the core and shells, with virtually no fusion occurring in the convective envelope. However, gravitational energy release from slow contraction of the core between burning stages can contribute significantly to total luminosity. As the star evolves and loses mass through winds, the envelope also contracts slightly, releasing additional gravitational energy. The total luminosity emerging at the photosphere, approximately 440,000 solar luminosities, represents the sum of all these contributions. Energy transport through the radiative layers is governed by the equation of radiative transfer, which balances energy absorption and emission at each radius. The opacity, which depends on temperature, density, and composition, determines how far photons can travel before being absorbed. In the core and inner envelope, electron scattering dominates opacity. In cooler outer regions, bound-bound and bound-free transitions of partially ionized atoms dominate. Near the photosphere, molecular absorption by Q, H2O, and other molecules contributes. Accurate opacity tables, calculated using atomic physics and compiled from laboratory measurements and quantum mechanical calculations, are essential for modeling stellar structure. Convective energy transport follows different physics. The mixing length theory, a semi-empirical framework developed in the mid-20th century, describes convection as a process where blobs of gas rise a characteristic distance, the mixing length, before dissolving and merging with surrounding gas. The mixing length is typically parameterized as a multiple of the local pressure scale height, the distance over which pressure drops by a factor of E. For red supergiants, the mixing length parameter is calibrated by comparing model predictions to observations of stars with known properties. Modern three-dimensional hydrodynamic simulations are beginning to replace mixing length theory for the largest and most evolved stars. These simulations solve equations of fluid dynamics on a three-dimensional grid, explicitly calculating convective flows without relying on parameterizations. Results show that red supergiant convection is highly complex, with large-scale cells, smaller turbulent eddies, and strong interactions between convection and pulsation. Convective cells are not symmetrical but show irregular shapes and time-varying patterns. Velocities vary spatially, with upflows concentrated in narrow lanes and downflows spread over broader areas. The internal rotation profile is poorly constrained. The envelope's slow rotation at the surface, if typical of red supergiants, might suggest approximately solid body rotation throughout the envelope. However, the core could rotate much faster, retaining angular momentum from earlier evolutionary phases despite mass loss that removes angular momentum from the envelope. Differential rotation, where different layers rotate at different rates, creates shear that could generate magnetic fields through dynamo action. Modeling rotation in stellar interiors requires solving angular momentum transport equations including effects of convection, meridional circulation, and magnetic torques, a challenging problem still under active research. Magnetic fields in red supergiant interiors are likely weak and tangled. Convective turbulence generates small-scale magnetic fields through stretching and twisting of field lines, but these fields may not organize into large-scale structures. Any fossil field remaining from earlier evolutionary phases would be wound up by differential rotation, creating toroidal field components. Magnetic buoyancy could cause field lines to rise and emerge at the surface, creating magnetic active regions analogous to sunspots but on far larger scales. Observational evidence for magnetic fields in red supergiants is limited, but some stars show spectropolarimetric signatures consistent with fields of a few Gauss. The transition region between the star and space is gradual, not sharp. The photosphere, defined as the layer where optical depth equals 2/3, is perhaps a few thousand kilometers thick, far larger than solar photosphere's few hundred kilometers but still negligible compared to the star's overall radius. Above the photosphere may exist a chromosphere, a layer of somewhat higher temperature than the photosphere proper, detected through emission lines in ultraviolet or visible spectra. Some red supergiants show strong chromospheric emission, suggesting heating mechanisms like shock waves from convection or acoustic waves generated in the turbulent envelope. Even higher in the atmosphere, material begins to escape as stellar wind. The wind acceleration zone extends from just above the photosphere to perhaps several stellar radii, where gas accelerates from thermal velocities around 5 km per second to terminal velocities around 15 to 30 km per second. Radiation pressure on spectral lines, particularly from metal ions, drives this acceleration. Once material reaches escape velocity, it streams outward, never to return, carrying mass and angular momentum away from the star and gradually eroding the envelope. Mass loss dynamics Stephenson 218 is dying, slowly shedding its outer layers into space through a powerful stellar wind that carries away several Earth masses of material every million years. This mass loss fundamentally shapes the star's evolution, determines how large it can become, and creates an extensive circumstellar environment that will eventually become a supernova remnant. Understanding the mechanisms driving mass loss and the structure of the circumstellar material provides crucial insights into the star's current state and future fate. Red supergiant and hypergiant winds are driven by radiation pressure, the outward force exerted by photons as they stream from the star's interior toward the surface. In the photosphere and lower atmosphere, photons are absorbed by atoms and molecules, transferring momentum. For absorption to drive significant acceleration, opacity must be high. In cool red supergiant atmospheres, partially ionized metals, particularly iron with its numerous energy levels and spectral lines, provide this opacity. Photons resonantly scatter off iron ions, being absorbed and re-emitted many times, each interaction imparting outward momentum. The process, called line-driven winds, was first understood in the context of hot massive stars where similar mechanisms operate at much higher velocities. For red supergiants, the physics is complicated by low temperatures allowing molecules to form, by dust condensation in the outer atmosphere, and by pulsation and convection creating density and velocity fluctuations. Current models combine radiative transfer calculations, hydrodynamics, and thermodynamics to predict mass loss rates from stellar parameters like luminosity, temperature, and composition. For Stephenson to 218, the mass loss rate is estimated at approximately K-6 to K-5 solar masses per year, though direct measurements are lacking. These estimates come from comparison with similar stars where mass loss has been measured through thermal radio emission from the wind, through infrared excess from circumstellar dust, or through spectroscopic signatures of outflowing material. At a rate of 10 to 6 solar masses per year, the star loses 1 solar mass every million years. Over its red supergiant lifetime of perhaps 1 to 2 million years, Stephenson the 2nd to the 18th of May have ejected several solar masses, reducing its total mass significantly from its main sequence value. The terminal velocity of the wind, the maximum velocity material achieves far from the star, is estimated at 15 to 30 kilometers per second based on comparison with other red supergiants. This velocity exceeds the escape velocity at the photosphere, which is approximately 12 kilometers per second for a star of Stephenson to 218's mass and radius. The fact that terminal velocity exceeds escape velocity is necessary for mass loss to occur. Material must reach escape velocity to leave the star permanently. Radiation pressure provides the additional acceleration needed to boost material from thermal velocities around 5 kilometers per second to escape velocity and beyond. The mass loss is not spherically symmetric. Observations of other red supergiants using interferometry and high-resolution imaging show asymmetries and clumpiness in their winds and circumstellar environments. Convective cells reaching the surface create density enhancements where more material is levitated into the acceleration region. Pulsation, if present, causes episodic increases in mass loss as the star expands and material in the extended atmosphere finds itself further from the center, experiencing weaker gravity. Rotation, even if slow, creates equatorial polar asymmetry, with potentially higher mass loss from the equator where centrifugal force reduces effective gravity. Dust formation in the wind dramatically affects mass loss efficiency. As material flows outward and cools below approximately 1,500 Kelvin, molecules like H2O, and CO form. At lower temperatures around 1,000 Kelvin, solid grains condense, primarily silicates compounds of silicon and oxygen and aluminum oxide. Dust grains have much larger absorption cross-sections than atoms or molecules, making them highly efficient at absorbing radiation. Photons absorbed by dust grains transfer momentum, accelerating the grains. The grains collide with gas atoms, dragging the gas along. This dust-driven wind can be far more effective than line-driven winds alone. The circumstellar environment around Stephenson to 218 has not been mapped in detail due to the star's faintness and distance. But observations of similar stars provide a template for what probably exists. At a distance of a few stellar radii, roughly 3 to 5 billion kilometers from the star, dust has condensed and the wind is well established. The density here might be around 105 hydrogen atoms per cubic centimeter, many orders of magnitude higher than the interstellar medium but still an excellent vacuum by terrestrial standards. Temperature has dropped to perhaps 500 to 1000 Kelvin, warm enough to glow in mid-infrared wavelengths. Further out, at 10 to 20 stellar radii, the wind continues expanding and cooling. Density falls as the material spreads over an increasing area, proportional to radius squared. By this distance, temperatures have dropped below 500 Kelvin, and the material emits primarily in far infrared and submillimeter wavelengths. Complex molecules may form, including polycyclic aromatic hydrocarbons (PAHs) and even simple organic compounds, though the harsh radiation environment limits chemical complexity compared to cool molecular clouds. At hundreds of stellar radii, approximately 1 light-year from the star, the stellar wind begins interacting with the surrounding interstellar medium. Stephenson 218 resides in a star cluster, so the interstellar medium here is actually intracluster material, gas between stars within Stephenson 2. The cluster likely has higher densities than typical interstellar space due to stellar winds from its 26 red supergiants and previous supernovae from stars that have already exploded. The collision between Stephenson 218's wind and this ambient material creates a bow shock if the star is moving through the cluster gas, or a contact discontinuity if the star is stationary relative to the gas. Evidence for episodic mass loss comes from observations of other red supergiants showing clumpy circumstellar structures. UY Canis Majoris, for example, has been extensively studied with high-resolution infrared imaging revealing knots, arcs, and filaments in its circumstellar nebula. These structures indicate discrete mass ejection events occurring over the past several thousand years, possibly triggered by convective eruptions or thermal pulses. Similar structures probably exist around Stephenson 218 but remain undetected due to observational limitations. The total mass in the circumstellar environment can be estimated from the mass loss rate and the time material takes to drift away. If the wind has been operating at 10 to 6 solar masses per year for 1 million years, approximately 1 solar mass has been ejected. This material now occupies a volume extending perhaps 1 to 10 light-years from the star, depending on wind velocity and how long the wind has been active. The average density is extraordinarily low, but the total mass is substantial, comparable to the mass of the star's current envelope. This circumstellar material will play a crucial role when Stephenson 218 explodes as a supernova. The supernova shock wave will plow through the circumstellar medium, sweeping it up and heating it to millions of Kelvin. The interaction will produce strong X-ray and radio emission, and the deceleration of the shock as it encounters denser material will affect the supernova light curve. Observations of the supernova's interaction with circumstellar material will provide information about the star's mass loss history over the final million years before explosion, a fossil record of the star's dying phase. Mass loss also affects the star's internal evolution. Removing mass from the envelope reduces the gravitational force compressing the core, allowing the core to expand slightly. This expansion reduces core temperature, which affects fusion rates. The balance between fusion heating and energy loss through neutrinos and photons shifts, potentially triggering transitions between different burning stages. Additionally, mass loss removes angular momentum, thinning down the star and affecting rotational mixing of chemical elements. Theoretical models of red supergiant evolution must include mass loss prescriptions to reproduce observed properties. Early models without mass loss predicted that massive stars would become even larger, potentially exceeding 5,000 solar radii. Observations showed this does not occur, indicating mass loss must be removing the outer envelope. Modern models include semi-empirical mass loss formulas calibrated to observations, adjusting mass loss rates based on luminosity, temperature, and other parameters. The results match observed red supergiant populations reasonably well, though uncertainties remain large. For Stephenson 218 specifically, the mass loss history is unknown. The star could be in a quiescent phase with relatively steady mass loss, or it could be undergoing enhanced mass loss due to pulsational instability or a thermal pulse. The star might have recently experienced a major ejection event, creating a detached shell of material now drifting outward. Without long-term monitoring or high-resolution imaging of the circumstellar environment, these possibilities cannot be distinguished. The fate of material ejected by Stephenson 218 depends on its composition and the radiation environment. Material rich in refractory elements like silicon, oxygen, and iron will remain as dust grains, eventually becoming incorporated into the interstellar medium and perhaps participating in future star formation. Material rich in volatile elements like carbon and nitrogen will remain gaseous or form molecules. The intense radiation from the star and from other stars in the cluster will photonize some of the gas, creating an H2 region around the cluster. Supernovae from other cluster members will send shock waves through the region, compressing and heating material. Over millions of years after Stephenson 218 explodes, its ejecta will mix with the cluster's other supernova remnants and stellar wind material, enriching the intracluster medium with heavy elements. If the cluster has sufficient gas density, this enriched material might trigger new star formation, creating a second generation of stars with higher metallicity than the first. More likely, the cluster will disperse, its stars scattering through the galactic disk, and ejected material will gradually mix into the general interstellar medium, contributing to the slow chemical evolution of the galaxy. Understanding mass loss in red supergiants like Stephenson 218 remains an active research area. Observations with next-generation facilities, including the James Webb Space Telescope's infrared capabilities and future extremely large telescopes, will map circumstellar environments in unprecedented detail. Hydrodynamic simulations of convection-driven mass loss are becoming more sophisticated, incorporating three-dimensional effects and realistic opacities. The combination of improved observations and better theory will eventually provide a comprehensive picture of how the largest stars lose mass and how this mass loss affects their evolution and ultimate fate. Evolutionary pathway. The journey that transformed Stephenson 218 from a newly formed massive star into the enormous red hypergiant we observe today spans approximately 14 to 20 million years. A long time by human standards, but a brief moment in cosmic history. Understanding this evolutionary pathway requires tracing the star through multiple distinct phases, each characterized by different fusion processes, structural configurations, and surface properties. The pathway depends critically on the star's initial mass, its metallicity, and the rate at which it loses mass through stellar winds, all of which influence whether a massive star ends its life as a compact blue supergiant, an extended red supergiant, or something in between. Stephenson 218's story began in a giant molecular cloud, a cold, dense region of interstellar space where gas and dust accumulated under gravity. The cluster Stephenson formed when this cloud became gravitationally unstable and fragmented into thousands of collapsing cores. The most massive cores, containing 20 to 30 solar masses of material, collapsed fastest due to their strong self-gravity. Within a few 100,000 years, the central temperature and density in Stephenson 218's progenitor core reached the threshold for hydrogen fusion, approximately 10 million Kelvin. And a new star was born. The newborn star, now on the main sequence, was radically different from the current object. With a radius of perhaps 15 to 20 solar radii, it was 100 times smaller than today. The surface temperature exceeded 30,000 Kelvin, making the star appear brilliant blue-white. The luminosity was already high, perhaps 100,000 to 150,000 solar luminosities, but lower than the current 440,000. The star's spectrum showed strong ultraviolet emission and absorption lines from ionized helium and other highly ionized species. Powerful stellar winds, driven by the intense ultraviolet radiation, were already beginning to erode the surface, though at a lower rate than today. For the next 8 to 10 million years, the star burned hydrogen in its core via the CNO cycle. This process fuses four hydrogen nuclei into one helium nucleus, using carbon, nitrogen, and oxygen as catalysts. The CNO cycle dominates over the proton-proton chain in massive stars because its reaction rate increases sharply with temperature, becoming more efficient than the proton-proton chain above about 18 million Kelvin. The core temperature in Stephenson 218's main sequence phase likely exceeded 30 million Kelvin, making CNO fusion overwhelmingly dominant. As fusion converted hydrogen to helium, the core's mean molecular weight increased. Helium nuclei are heavier than hydrogen nuclei, so the same mass occupies less volume at the same temperature and pressure. The core gradually contracted, increasing its temperature and density. This contraction accelerated fusion rates, causing the star's luminosity to increase slowly over the main sequence lifetime. By the end of hydrogen burning, the luminosity may have increased by 30 to 40% from its initial value. When core hydrogen was exhausted, fusion ceased in the central region. The core, now composed of helium, began contracting under gravity. This contraction released gravitational energy, heating the core and the surrounding hydrogen-rich layers. As the temperature in the shell surrounding the core exceeded 30 million Kelvin, hydrogen fusion ignited there. The star now derived its energy from a shell source rather than central fusion, a configuration that would persist for the rest of its life with progressively more shell sources added at different radii as evolution continued. The transition from core hydrogen burning to shell hydrogen burning triggered a dramatic transformation. The increased energy generation from the hydrogen burning shell drove a rapid expansion of the envelope. Over perhaps 100,000 years, the radius swelled from 20 solar radii to several hundred solar radii, and the surface temperature dropped from 30,000 Kelvin to below 10,000 Kelvin. The star transitioned across the Hertzsprung-Russell diagram from the blue main sequence to the red supergiant branch, changing color from blue to yellow to orange to red as the expansion and cooling continued. This expansion occurred because the envelope's opacity increased as temperature dropped. Cooler temperatures allowed partial ionization of hydrogen and helium, creating conditions where radiation could not efficiently transport the enormous energy flux from the shell burning. Convection developed throughout the envelope, extending from just above the hydrogen-burning shell all the way to the surface. Convective energy transport required a large temperature gradient, achieved through expansion to a large radius. The envelope continued expanding until it reached a size where convective transport could carry the luminosity to the surface. When the helium core reached a mass of approximately 2 for solar masses and a temperature near 100 million Kelvin, helium fusion ignited through the triple alpha process. 3 helium nuclei combined to form carbon, releasing energy. The ignition happened relatively smoothly for a star of Stephenson to 218's mass, and like lower mass stars where helium ignition occurs in a runaway flash. The energy from helium burning provided additional support against gravity, possibly causing the envelope to contract slightly or at least halting further expansion. The helium core burning phase lasted approximately 1 million years, during which Stephenson to 218 remained a red supergiant with properties similar to its current state. The star's position on the Hertzsprung-Russell diagram during this phase is called the red supergiant branch or the asymptotic giant branch for intermediate mass stars. During this time, mass loss through stellar winds became significant, driven by the star's high luminosity and low surface gravity. Pulsation may have developed, with the star varying in radius and brightness on timescales of months to years. As helium in the core depleted, the pattern repeated. The helium core became inert carbon and oxygen, fusion continued in helium and hydrogen shells at different radii, and the core contracted further. Carbon fusion ignited at about 600 million Kelvin, lasting approximately 12,000 years. The star may have undergone thermal pulses during this phase, episodic reignition of helium in a shell causing temporary increases in luminosity and radius, though this behavior is more common in lower mass stars and less certain for stars of Stephenson to 218's mass. Current evolutionary models suggest Stephenson to 218 is now in the post-helium burning phase, possibly undergoing carbon, neon, or oxygen fusion in the core. Each successive stage lasts shorter than the previous one because fusion of heavier elements releases less energy per unit mass while the star's energy demands remain high. The star is racing towards silicon fusion, the final stage before core collapse. The core now probably contains an onion-like structure with concentric shells of different composition, iron and silicon at the center, surrounded by shells enriched in oxygen, neon, carbon, helium, and finally hydrogen in the outermost layer. The evolutionary pathway from main sequence to current state involved critical decision points where the star's future was determined. One key factor was mass loss. If Stephenson to 218 had lost mass more rapidly during its main sequence and early red supergiant phases, it might have been stripped of its hydrogen envelope entirely, becoming a Wolf-Rayet star, a hot compact object with exposed helium or carbon layers. Wolf-Rayet stars eventually explode as type Ib or type Ic supernovae, which lack hydrogen in their spectra. The fact that Stephenson to 218 retains a massive hydrogen envelope indicates mass loss, while significant, was not extreme enough to strip the envelope. Another critical factor was rotation. Rapidly rotating massive stars experience rotational mixing, where rotation-induced instabilities transport material between core and envelope, dredging up fusion products and bringing fresh hydrogen into the burning regions. This extends the main sequence lifetime and affects subsequent evolution. Stephenson 218's rotation is unknown, but if the star is a slow rotator like most red supergiants, rotational mixing probably played a minor role in its evolution. Metallicity, the fraction of the star's mass in elements heavier than helium, also influenced evolution. Higher metallicity increases opacity, which affects stellar winds and envelope structure. Stephenson 218 probably has near-solar metallicity based on its location in the galactic disk at a similar distance from the galactic center as the Sun. This metallicity makes line-driven winds efficient, contributing to mass loss, but not so high that the envelope became unstable during early evolutionary phases. Binary interactions could have affected evolution if Stephenson 218 had a close companion star. Mass transfer from one star to another, or merger of two stars, can dramatically alter evolutionary pathways. No evidence exists for a close companion to Stephenson 218, though this has not been thoroughly investigated. The star likely evolved as a single star, though a distant wide-orbit companion is possible, and would not have affected the evolution significantly. Comparing Stephenson 218's evolutionary pathway to other massive stars reveals diversity. Some massive stars become luminous blue variables, showing extreme variability and episodic mass loss events. Others become yellow hypergiants, occupying a narrow temperature range between blue and red supergiants. Still others explode as supernovae directly from the blue supergiant phase without becoming red supergiants. The factors determining which path a star follows include mass loss rate, rotation, metallicity, and possibly stochastic events like convective eruptions or interactions with companions. Stephenson 218 followed the pathway to red supergiant status, likely because its mass at the end of helium burning remained high enough to sustain a massive envelope yet low enough after main sequence. Mass lost that the envelope became convectively unstable and expanded. Had the star been slightly more massive initially, it might have lost its envelope and become a Wolf-Rayet star. Had it been slightly less massive, it might have remained a less extreme red supergiant, not reaching the enormous size we observe. The evolutionary models predicting these pathways are sophisticated, solving coupled differential equations describing stellar structure, energy generation and transport, composition changes from fusion and mixing, and mass loss. The models are calibrated to observations of stars at various evolutionary stages and validated by reproducing the properties of star clusters where many stars of similar age, but different masses can be studied simultaneously. Despite their sophistication, the models contain uncertainties, particularly in the treatment of convection, mass loss, and rotation, leading to spreads in predicted properties even for stars with identical initial conditions. For Stephenson 218, models suggest the star will remain a red supergiant for perhaps another 100,000 to 1 million years before core collapse, though the uncertainty is large. The star could explode as soon as tomorrow if it is in late silicon burning, or it could survive for another million years if it has just begun oxygen burning. Once silicon fusion begins in the core, the countdown to supernova becomes a matter of days or weeks, not years. The final evolutionary stages proceed so rapidly that the probability of observing a star in silicon burning is vanishingly small, explaining why we have not yet witnessed a supernova from a star we were monitoring before. Explosion. Except for SN 1987A, where the progenitor was identified in pre-explosion images but not actively monitored. Supernova destiny. The ultimate fate awaiting Stephenson 218 is catastrophic destruction in a core collapse supernova, one of the most violent explosions the universe produces. When the iron core forming at the star's center reaches the Chandrasekhar limit of approximately 1 point for solar masses, electron degeneracy pressure will fail catastrophically, and the core will implode at velocities approaching 70,000 kilometers per second. Within less than 1 second, the core will collapse from roughly the size of Earth to a sphere 20 kilometers in diameter, rebounding to launch a shockwave that tears through the star's overlying layers. The explosion will scatter Stephenson 218's carefully synthesized elements across light years of space, enriching the interstellar medium and leaving behind either a neutron star or possibly a black hole. The path to core collapse begins with silicon fusion, the final nuclear burning stage. At temperatures exceeding 3 billion Kelvin, silicon nuclei undergo a complex series of photodisintegration and capture reactions that progressively build heavier elements. The process does not directly fuse silicon into iron but rather breaks silicon into helium and free neutrons through energetic photons, then reassembles these components into progressively heavier nuclei. Over approximately 1 week, the core converts silicon into elements clustered around iron-56 and nickel-56, the most stable nuclei in terms of binding energy per nucleon. Iron-56 represents an energetic dead end. Fusing iron into heavier elements requires energy input rather than releasing energy. The nuclear binding energy curve peaks at iron. Nuclei lighter than iron release energy when fused together, while nuclei heavier than iron release energy when split apart. When the core becomes primarily iron, fusion as an energy source ceases. The star has no mechanism remaining to generate the pressure needed to support the overlying 15 or more solar masses of material pressing inward under gravity. Two processes then combine to destroy the core's pressure support. Photodisintegration begins when core temperatures exceed 10 billion Kelvin. High-energy photons have enough energy to break apart iron nuclei into helium nuclei and free neutrons. This endothermic process absorbs energy, approximately 124 million electron volts per iron nucleus destroyed, removing thermal energy from the core. Simultaneously, electron capture or inverse beta decay becomes significant. Electrons combine with protons to form neutrons and neutrinos. The neutrinos, barely interacting with matter, escape the core immediately, carrying away energy and reducing pressure support. Both processes reduce pressure catastrophically. Temperature drops as photodisintegration absorbs energy. Electron pressure drops as electrons disappear. With pressure falling and gravity unchanged, the core begins to collapse. The collapse accelerates rapidly. Within 100 milliseconds, the inner core, about half a solar mass of material, shrinks from roughly Earth size to 15 kilometers in diameter. The infalling material reaches velocities of 70,000 kilometers per second, nearly 1/4 the speed of light. When the collapsing core reaches nuclear density, approximately 500 trillion kilograms per cubic meter, neutrons begin touching each other and the strong nuclear force becomes repulsive. The core suddenly becomes incompressible, like a ball compressed to its absolute limit. The infalling material slams into this newly rigid core and rebounds. The rebound launches a shockwave outward through the still collapsing outer core and the overlying stellar layers. The shock initially carries enormous energy, perhaps kilojoules, seemingly sufficient to blow apart the star. However, as the shock moves outward, it encounters dense material still falling inward and dissociates iron and silicon nuclei, consuming energy. Within milliseconds, the shock stalls at a radius of a few hundred kilometers. Losing its energy before reaching the star's surface, the supernova appears to fail. What revives the shock is neutrino heating. The proton-neutron star at the center, incredibly hot at 100 billion Kelvin or more, radiates neutrinos of all flavors: electron, muon, and tau neutrinos and their antiparticles. Over about 10 seconds, the proton-neutron star emits approximately 1,046 joules in neutrinos, 99% of the gravitational binding energy released during core collapse. Most of these neutrinos escape without interaction, but a small fraction, roughly 1%, deposit their energy in the region behind the stalled shock, heating the material there. This neutrino heating gradually increases temperature and pressure behind the shock, reviving it. After a few hundred milliseconds of stalling, the shock begins moving outward again. Aided by convective instabilities that develop in the heating region, the shock accelerates through the overlying layers. The process is sensitive to details like the core's rotation, magnetic fields, and the neutrino interaction physics. Small changes can mean the difference between successful explosion and collapse to a black hole. For Stephenson 218, current models suggest successful explosion is likely. The star's core mass at collapse, determined by its initial mass and the amount of mass lost through winds, is probably in the range where neutrino heating can revive the shock. Stars that are too massive, with core masses exceeding about 25 solar masses at collapse, may fail to explode, instead collapsing directly to black holes. Stephenson 218's current mass of 12 to 18 solar masses makes successful explosion probable, though not certain. If the explosion succeeds, the revived shock takes approximately 2 hours to propagate through Stephenson to 218's extended envelope, traveling 1.5 billion kilometers from the core to the surface. When the shock breaks through the photosphere, it creates a brilliant flash of ultraviolet and X-ray radiation called shock breakout. This flash lasts only seconds and would be extremely difficult to detect for a supernova at 19,000 light-years, requiring X-ray telescopes pointed at exactly the right location at exactly the right time. Following shock breakout, the supernova enters the photospheric phase. The expanding ejecta, heated to millions of Kelvin by the shock passage, cool as they expand and begin emitting optical light. The supernova brightens rapidly, reaching peak luminosity within about 2 weeks. At peak, Stephenson to 218 supernova will shine with approximately 100 million to 1 billion solar luminosities, briefly outshining entire galaxies. From Earth, the supernova will appear as a new star, visible to the naked eye with an apparent magnitude around +8 to +9, too faint for naked eye visibility but easily observable with small telescopes. The light curve, the supernova's brightness over time, will follow a characteristic shape. After reaching peak, the brightness will decline exponentially with a half-life of approximately 77 days, matching the radioactive decay of cobalt-56 to iron-56. Cobalt-56 is produced from the decay of nickel-56 synthesized in the explosion, and its decay releases gamma rays that thermalize in the expanding ejecta, heating it and causing optical emission. As the ejecta expand and become more transparent, the decline rate steepens. The spectrum will show strong hydrogen emission lines, identifying this as a type II supernova. The hydrogen comes from the massive envelope that Stephenson to 218 retained despite millions of years of mass loss. Different subtypes exist within type II. Type IIp supernovae show a plateau in their light curves lasting several months, while type II will show linear decline. Stephenson 218 supernova could be either, depending on envelope mass and structure at the time of explosion. The enormous envelope mass might produce a long-lasting plateau as recombination of hydrogen keeps the photosphere optically thick for an extended period. The supernova will also be visible at other wavelengths. X-ray emission will come from the shock interaction with circumstellar material, the wind-blown bubble Stephenson to 218 created over millions of years. As the shock plows into this material, it will heat it to tens of millions of Kelvin, producing X-rays detectable by space-based X-ray telescopes. Radio emission will develop as the shock accelerates electrons to relativistic velocities, creating synchrotron radiation. Infrared emission will appear as dust forms in the cooling ejecta several months to years after explosion. Neutrino observatories on Earth will detect the neutrino burst from core collapse. At 19,000 light-years, Stephenson to 218 is about 3 times closer than the small Magellanic Cloud where supernova 1987A occurred, the only core collapse supernova from which neutrinos have been detected so far. Modern neutrino detectors like Super Kamiokande in Japan and ISECube in Antarctica are far more sensitive than the detectors operating in 1987. They would detect thousands to tens of thousands of neutrinos from Stephenson to 218 supernova, providing unprecedented data about the core collapse process. The remnant left behind depends on the final core mass. If the core mass after explosion is below approximately 2.5 solar masses, the remnant will be a neutron star, an object composed almost entirely of neutrons with a radius around 10 to 15 kilometers and a mass of 1.42 solar masses. The neutron star will be incredibly dense, with a teaspoon of neutron star material weighing about 10 million tons. It will rotate rapidly, perhaps hundreds of times per second, a rate determined by conservation of angular momentum as the core collapsed from Earth size to city size. If the neutron star has a strong magnetic field, it will shine as a pulsar, emitting beams of radio emission from its magnetic poles. As the star rotates, These beams sweep across space like a lighthouse. If one beam points toward Earth, we detect regular pulses of radio waves, one per rotation. The Crab Nebula's pulsar, remnant of the 1050 for supernova, rotates 30 times per second and is slowing down as it radiates energy. Stephenson to 218's pulsar would likely be detectable for thousands of years after the supernova, gradually slowing as it loses rotational energy. Alternatively, if the core mass exceeds approximately 2.5 to 3 solar masses, neutron degeneracy pressure cannot support it, and continued collapse to a black hole becomes inevitable. The black hole would form within seconds to minutes after the initial bounce, after neutrino emission has ceased. The collapsing material would cross the event horizon, disappearing from view. From outside, the black hole would appear as a dark object, detectable only through its gravitational effects on nearby matter or companion stars. If Stephenson to 218 forms a black hole, it would have a mass of 3 to 5 solar masses, adding to the population of stellar mass black holes in the galaxy. Current uncertainties in supernova physics make predicting which outcome occurs difficult. The boundary between neutron star and black hole formation is not sharp but depends on the equation of state of nuclear matter at extreme densities, the efficiency of neutrino heating, and the amount of fallback material that returns to the core after the initial explosion. Stephenson to 218 sits near the boundary, making its ultimate fate genuinely uncertain. The supernova will enrich the interstellar medium with heavy elements. Approximately 10 to 15 solar masses of processed material will be ejected at velocities exceeding 10,000 kilometers per second. This ejecta contains hydrogen and helium from the envelope, carbon and oxygen from helium burning, silicon and sulfur from carbon and oxygen burning, and iron peak elements from silicon burning and explosive nucleosynthesis during the supernova itself. Radioactive isotopes including nickel-56, cobalt-56, and titanium-40 for decay over weeks to years, powering the supernova's late-time emission and contributing to nucleosynthesis. The expanding supernova remnant will interact with Stephenson to 218's circumstellar environment and eventually with the general interstellar medium. Over thousands of years, the remnant will cool, forming a supernova remnant visible at X-ray, optical, and radio wavelengths. The Crab Nebula, Cassiopeia, and other famous remnants show what Stephenson to 218's remnant might look like, glowing filaments of shock gas, enriched with heavy elements, expanding through space and triggering new generations of star formation where the shock compresses surrounding clouds.